Hi there. Today we're looking at synthetic Petri dish, a novel surrogate model for rapid architecture search by Adi Tarawal, Joel Lehman, Felipe Petrowski-Such, Jeff Clune, and Kenneth O. Stanley. This paper, on a high level, it basically says if you want to do neural architecture search, if you, for example, search for a better nonlinearity, you should be able to extract that nonlinearity instantiated in a very small network and then evaluate that very small network in order to predict the performance of a large network. And therefore, you can find a better nonlinearity in much less time. Now, the exact procedure, how you do this in the small network, is the topic of this paper. As always, if you like content like this, I encourage you to subscribe if you are not already, and to share out the video so other people can experience the joy themselves. All right, let's dive in. So they say in the abstract, neural architecture search explores a large space of architectural motives, which basically... So it basically means you want to find a neural architecture. Let's say you have a multi-layer perceptron right here, a couple of layers, okay? And they're all connected by, feed-forward weights, whatnot. And each of these weights basically is a multiplication. So each one of these is a multiplication of x by your weight, w. And then there is a nonlinearity. So the nonlinearity could be a sigmoid. So the sigmoid would be something like 1 over 1 plus e to the negative x. Now there's a bit of an extension in a sigmoid where you can do a sigmoid that has like a temperature parameter attached or a slope parameter where you go cx. So in one case you can set c such that the sigmoid has a shape like this. And then if you put c to a different value, you can make this slope, you can make it like a shape. Well, this is terrible. Like this. You know what I mean. Okay, so this c right here can potentially change the behavior of your network. And you want to find a good parameter c, and this is a hyperparameter. Now, there are many hyperparameters like this. For example, how many units you have in a particular layer. In a CNN, it could be your filter size. In a transformer, it could be the number of heads and so on. It could actually be not only the slope of the nonlinearity, but the actual nonlinearity itself. Or famously, in recurrent neural networks, you have these recurrent cells, and they're like, okay, we have an input signal and a carry signal, and then the input here is like dot multiplied here, and then there is like a gate with a nonlinearity, and then it's kind of like multiplied by the carry, but then there's also a forget gate and whatnot. There's a minus right here. It's very complicated, and so people do architecture search over these kind of problems to find better architectures for particular problems. Now, the problem is, of course, that how do you know if a given architecture is good? What you have to do is you'll have to go take that cell that you have dreamed up. You think, well, I think that's a good cell, and you have to train it on the full training data set. This is a data set, a database, right? This is the full training data set. Then you need to evaluate it on your validation data set, and then you have like a number. You have like, okay, this is 8 good. And then you go back and you say, okay, what if I change this cell here? What if I change it to a plus instead of a minus? And you do the entire thing again, train it for I don't know how much, validate it, and then this is like a 9. And you can say, oh, cool, that's a 9. So this is the very basic architecture search. And there has been a lot of development in this space, so like evolutionary search and so on, but most of the time they require pretty much evaluating the entire thing on the full data, so you get a good estimate of what your final performance back here is going to be. Now, people have come up with methods to counter that, and they say, well, if we can sort of encode the cell structure, let's go with the RNN cell. If we could encode the cell structure in a sort of a continuous way. So, we can encode text in a continuous way. We could also encode a cell structure, because this cell structure, I can write it down as an equation. I can say like, okay, it's the forget gate of the carry times the sigmoid output of x plus the, so this is the plus here, and plus the sigmoid output of x multiplied by the input, let's call that I, something like this, right? This is text. I can like write it down, and then I can encode that into a vector. I can, for example, build another RNN, ironically, or something to encode that, or I can represent it as a computation graph like it is here, and use a graph neural network to encode that into a single vector. And then I have sort of an embedding space where each cell that I could build is a point in that embedding space. And then I can evaluate a couple of them. I can, for example, say, okay, this one here, this one here, this one here, this one here. I'm going to train them, these cells. I'm going to do the full training, eval, and so on, get their scores. And then I can learn, basically in this latent space, I can learn a predictor. I can say, okay, here I got an 8, I got a 9, I got a 2, and I got a 4. So it appears to be that in this direction, the good cells are in this direction. And then I can do it again. I can sample, or I can do gradient descent in this space. Since this is now a continuous space, I can do gradient descent on the model that gives me this space. So right, so this method basically tries to take in the building plan of a cell and learn to predict the performance just by looking at it. If you're thinking of a Turing machine right now, then I immediately thought of like this halting problem because it appears to be exactly what it is. So you're trying to build a machine that takes the building plan of another machine and tries to predict its performance. Now, in a general sense, we can already state that this problem is sort of the difficulty of this problem is equivalent to the difficulty of the original problem. So I'm not sure, but it appears to work if you throw lots of compute at it. But of course, that's a problem. You need lots of compute, right? So either your option one is to run all of these things and kind of iterate them in a in an evolutionary way, or your second option is to take the building plan and predict the performance from that. Both are not satisfactory and both use lots of compute. Now, neural Petri dish synthetic Petri dish is a way to combine the two together. It says, can we take the building plan here, but actually run on the data to predict the performance? So what they're saying is basically, if I have this cell right here, and usually this cell, it deals with vectors of, let's say, size 512 and so on. It will say, since this is, let me draw it again up here. So here you have the cell, and here you have somehow the connections in there, the carry and the input here. Okay, and this is the output or the carry. I have 512 embedding, like size of this. So this is a giant cell. There's 512, the vector has 512 dimensions going in, basically. Can't I take the exact same thing, and keep the connection pattern? So I would keep the entire pattern of connection right here, but I only do it for 1 or 2. So this is 512, and this is just 2, right? It's just I just reduce the dimensionality, but I sort of keep the connection pattern alive. If I only do that, I have like a very small network right now. And the same goes for if this is, so a lot of times these RNNs, they have multiple layers of these things. So they have another exactly equal box up here and then another up here. I can just reduce this to one layer. And out of the regularity of these neural network things, it is known that, or one can make the assumption that the performance on this thing will kind of be correlated to the performance of the entire thing. And that's one of the things that this Petri dish paper does. So we try to take out what we are trying to search over, namely the connection pattern. We keep that as it is up here. But we reduce everything else. We reduce the dimensionality, we reduce the number of layers, and so on. Now, they don't actually reduce the number of layers here, but you can reduce the number of units and so on, okay? So this, in essence, this works whenever you can do that, whenever you can keep the structure you're searching over, but can reduce the rest. So that's one precondition. Doesn't work for everything. The second part here is that you don't want to use this particular training data and then this particular validation data. Because first of all, it's a lot of training data. And second of all, it won't give you that good of a prediction. Instead of what you're trying to do, and this is the second part of the idea of Petri dish, is you're trying to abstract the training data to get you a very small data set, such that, and the validation data as well, such that if you train on this data and evaluate on this data, the performance that you get will be very predictive of the performance had you trained the big model on the big data set, okay? In fact, in this Petri dish paper, these little data sets, they have nothing to do with the original train and validation data. And that's, I think that's one of the cool things here. These things, this training data and this validation data, they are optimized as well by the procedure. They're optimized special data points that are trained. These are trained parameters, such that if you train on the small training data and evaluate on the small eval data, you will be able to predict this performance back here with high accuracy. Okay, and this, I think, is where previous approaches have or might have failed, because it's, you know, the idea of scaling down your network in order to do the architecture search is probably has appeared to many people before. That's not, you know, that's not really a genius idea, but probably they have all found that now we can't really do it. It doesn't really give us accurate enough numbers. But in this case, the addition of adding these synthetic data sets that are much smaller, but can still, if you train and evaluate on them, can still predict with high accuracy the full score of the full model. That, I think, makes this idea work. All right, so I guess we're already through the idea and problem setting and everything without actually reading the paper. So they give this example right here at the beginning, that if you have a two-layer 100 wide, so 100 dimensional MNIST networks, it's two layers, I think it's an MLP, it's a two-layer MLP with a non-linearity that is this sigmoid right here, this. Okay, now you can see it has this temperature parameter here. It has this slope parameter, and you want to do neural architecture search to find the best slope parameter. Now, usually you would just do a grid search, but this is an example, because this can be, of course, much higher dimensional things, and then you don't want to do grid search anymore. Okay, so what do we do? If you look at how the 100 wide MNIST network, so we can draw it right here. So this is a 100 dimensional MNIST network. So this is 100. And each cell, each connection here first has a weight and then has the sigmoid nonlinearity. And this sigmoid nonlinearity is parameterized by the parameter C. Okay, and you have many of them, right? You have one here, and so on, and each one has a different C, and each of these networks represents one blue dot here. So if you let C vary, so this sigmoid slope value right here, that's your parameter C. If you let this vary and train the big network on the entire dataset to convergence, and then you eval on the validation dataset, you get the slope like the blue curve. So if you see the blue curve is, if you start over here, if you reduce this slope, you'll gain in performance, but if you reduce it too much, you drop drastically, okay? Until if it's zero, it's basically, you know, the X is not, the signal doesn't propagate anymore, and you have no learning occurring. Okay, so that's the original performance. Now, what if I only give you training data in this range right here? I only showed you this particular range. I can't actually zoom in that much. But if I give you this and I ask you to build one of these, please take the architecture and predict the performance that we saw at the beginning, like one of these Gödel machines or Turing machines, you would basically say, well, that looks to me like a line, so I'm going to predict the red thing here. And even if you can, evaluate a bunch of these, it just looks like a line, and you're going to predict it's probably a slope like this, right? This happens almost independently of which model you choose to predict right here. The data of training simply doesn't give away that the fact that there is this break down here, which happens in the real world. So if you just give this as training data, there's no way. So the criticism about these models is valid, that they will only work where you give them training data. They can at best interpolate their training data, but they can't really extrapolate. Now here, since the synthetic Petri dish method, which is the green thing here, uses the actual nonlinearity that this thing characterizes. So it instantiates the sigmoid with the parameter c that you give it, just not on the large network, but on a small network. In fact, their network is just one unit, and then another unit. So it's just a two hidden layer, but just with one unit instead of 100. And of course, you can't feed in MNIST right here, right? But we said they don't feed in the data. They actually feed in their synthetic data that they learn. So you give them the points here, and they learn the synthetic data to evaluate the others. And then once you ask them, well, if my C is right here, what's the performance going to be? It's going to instantiate that in its small network. It is going to use the training data that it has learned from this region right here in order to train this, and then it's going to evaluate this on the synthetic validation data that is also learned on the training data, and it is going to come up with a performance metric. It says, okay, this is how good it's going to be. And since it is an approximation in its building plan to the entire network, it will react similarly. So it will get that there is this performance dip right here. Okay, so you can see how this sort of makes sense. You're actually running an approximation to the actual program instead of just looking at the plan of the program and trying to predict it, which, halting problem says hello. Okay, so that is the motivating example of their MNIST thing, and here is the entire algorithm. All right, so you take MNIST training and validation data, and you instantiate a bunch of really big networks. This is ground truth, okay? You need this to learn from. You instantiate a bunch of really big networks. Now, if I draw the graph from before, right, we had, this was the performance of the actual networks. This comes from here, from this region right here. This is the training data. Okay, so you instantiate a bunch of these networks. Each one you instantiate in one of them, right? Each one gives rise to a different nonlinearity. And you do the full training, ground truth training and evaluation on the full training set and the full validation set, and you get validation losses, right, for each of these. And these are the points right here. Now, that's the training data for your neural architecture search, so for your Petri dish method. What the Petri dish does is, it says it extracts the motive, and the motive is the thing that you optimize over. So as I said, you want to keep that thing in its essence, but you want to reduce everything else. So it reduces it, instead of from a 2-layer 100 wide MLP, it reduces that to a 2-layer single neuron wide MLP, okay? And this over here is the training data for the procedure that we're going to do now. So what it would take is it would take one of these values, it would instantiate, and we have that here, it would instantiate the neural network in the small form of that. And now we know that if I train the full data and evaluate, if I train on the full training data and evaluate on the full validation data, I should get this accuracy. All right. So I will create, and we're going to look at in a second, I will create training and validation data such that if I train on this training data and then validate on this validation data, I get the same validation loss as if I had trained the big network with the same, the same C parameter on the full training data and evaluate on the full validation data. Okay, so in this step, I'm optimizing the data here, the training and validation data. All right, and now in the second step, once I have this training and validation data such that I can basically reproduce this graph right here, then I can go and actually ask my model, okay, now please tell me what happens over here. So what am I going to do? I'm going to take that, I'm going to instantiate it, I'm going to use my training data that I learned to train it, I'm going to use my validation data that I learned to evaluate it, and it's going to give me a number, and that number is going to be like close to, hopefully close to this. So this is how we can extrapolate using that method, okay? Now, there are a number of assumptions right here, and you can imagine this doesn't work in any situation. This works if you basically you have to get lucky in that you have to abstract the correct things, right? I said you need to reduce everything else, so they reduce, notably you see they reduce the 100 layer width to a single neuron wide MLP. And they sort of guess that doesn't change the fundamental thing. But you can also see they leave the 2-layer, right? They leave the 2-layer neural network. And I can almost guarantee you that they tried this, reducing this to a 1-layer neural network, and it did not work. And so you have to be sort of very careful of what quantities you abstract and what quantities you don't, because okay, now you might always think, oh, I can reduce the number of dimensions or channels. That's also not always the case. So I think that's kind of the crux of the method. You have to actually engineer this down compressing of the architecture such that its properties are still kept. And in other things, how do you actually produce training and validation data to match these? And there are a number of ways, but what comes to mind is meta learning, right? So because what you're doing, they initialize the training and validation data at random points. So these are just random at the beginning. And then they optimize the data itself using gradient descent. Okay, now see, synthetic training data, and they are randomly initialized. Okay, and they use gradient descent. They have it somewhere. Yes, so they have this inner training loop, okay, which is many steps of inner training. And then they have the outer loss, which is it's the validation loss after the inner training loop, and the difference from that to the true validation loss. And then they do gradient descent on this outer loss. Now, this outer loss is a result of the inner loss, and the inner loss is a result of the inner training procedure. And the inner training procedure is n steps of feeding in the training data. Every step you feed in the training data. So your computational graph is going to look like, so here's your training data, S-train, and here are your initial parameters. You initialize them randomly. In the first step, you use the training data to produce theta 1. Then in the second step, you use your training data again to produce theta 2. And then you use it again to use theta 3, and so on. Each time you feed the training data in order to evolve your parameters to give you better prediction, right? So the gradient, since somewhere back here there's a loss, the gradient here will have to flow back through all of these paths and through all of these connections to the training data. This is kind of, you back propagate through an optimization procedure. And we had this a bunch of times here. And I've looked at the code, and the code is like really crazy, and it looks like proper research code, but it appears to be that that's actually what's happening. They backprop through the optimization procedure to find this synthetic training and validation data. Now, that's that's crazy, but it also kind of limits how far you can go with this, because usually you can't backprop for more than a couple of steps doing this. Now, that the fact that the inner model is small helps, but also this introduces very, very much, like, these things are very brittle. If you backprop through an optimization procedure like this, these things tend to be very brittle. And so I think there's another thing there where you have to pay careful attention. All right. It's basically it. The last thing they say is that they can combine this with architecture search, in that, so not only can you predict good architectures, what you can do is you can actually predict which architectures are good, and then you can use that prediction to basically input this into your neural architecture search to inform it. So instead of the neural architecture search having to evaluate all of the candidates that it produces, it only has to now evaluate the very small subset of candidates that the synthetic Petri dish training deems most worthy of being evaluated. In this case here, instead of evaluating all of the things here, it would limit itself to whatever the synthetic Petri dish says are the highest performing ones. Because if the synthetic Petri dish is any good, then it will, give accurate predictions of how they're performing. And then that can go in multiple rounds. So the architecture search can come up with new things that it thinks are better through like an evolutionary mutation algorithm. The Petri dish can evaluate them in the synthetic way and then suggest the 10 candidates to evaluate on the full test set. And so that way you don't have to evaluate all the 1,000 candidates. All right. Cool. They do this for this MNIST, and they also do it for finding a RNN cell for the Petri bank. This is a language modeling task, and this is a benchmark for neural architecture search, where you're trying to find a good RNN cell to get the perplexity really low. And here you can see if they give the same amount of data to all the methods, then the benchmark neural architecture search is worse than the synthetic Petri dish informed architecture search. Now, one has to say on the full data, I believe the NAO gets to about here, but of course, if you give all of them the same data, the Petri dish beats this method. And I think still this method here uses way more compute, because it always has to evaluate all the candidates. And that's exactly one of these where I learn an architecture to predict the other architecture by just looking at it. So it works, but it doesn't work as well as actually running the architecture in an abstract fashion. This also shows you the importance of selecting your experimental evaluation in a smart way. Like they argue for very long why it makes sense to evaluate everything on reduced data, such that their method here can be better, and they don't have to compare to the full thing. It's easier for them to work on reduced data, and they argue, it's what people usually do in practice, and that's the task they focus on. So, good paper writing right here. Yeah, that's basically it to the paper. There's a lot of things to be said here. I think this works in very, very limited settings. It seems to me that it's sort of brittle with respect to how you abstract, and also it's always the case, like how large is this synthetic training data? In their case, they abstract this to 20 or 30 data points or something like this. So it seems to me, since you're optimizing this training data with gradient descent, what you would mainly find are adversarial examples to this architecture here. So I'm going to guess that the inner optimization is very noisy, and that's because if you really let your optimizer run, then it will abuse every single thing it can to match that validation loss. And that will usually lead to an adversarial example since you're optimizing the data itself. Okay. So I think this suffers from that. And we had this in the planning, planning in learned world models in reinforcement learning, where if you have a really, really good planner, it will just abuse the mistakes that you make in approximating the true world. And the same here. You're going to make mistakes approximating this architecture here. And the better your optimizer is for producing this synthetic data, probably the worse the result is going to match, the worse that these losses are going to actually match. Now, okay, these losses will match because that's what you train for, but the worse these two curves will match each other, because now you're just finding adversarial examples for your particular training data. Another concern I have here is with respect to the double descent phenomenon. So if you know the double descent phenomenon, if here you have your number of parameters, and here you have your validation loss, let's say, and you know that if I add parameters, I can make my validation loss go down. So this is assuming I have a model with p parameters, and I always train it on the train data to convergence. Now, if I add parameters, I can generalize better until a point where I add too many parameters and I start overfitting. Then my validation loss goes up again. But the double descent phenomenon, and I think I've done a video on this, shows that after a certain threshold, you get the interpolation threshold. The validation loss goes actually down again and goes down even further here. Now, so this is a very strange phenomenon by itself, but I'm sort of concerned that if you do this abstraction that this paper proposes, so let's say your full model is here with a large number of parameters, so it is past this interpolation threshold. If you now seriously reduce the number of parameters because you want to go into this Petri dish, you will maybe you will cross this interpolation threshold and actually be on this side of the curve right here. Now, of course, at the same time, you reduce the amount of data, which would push you over here again, but it is different data, so I'm not sure how all of this is going to play out. It appears to work in these settings right here, but I think this is it's sort of applicable in some situations, and it'd be very cool if we develop this further, such that we understand when it applies and when we can use it, because I feel this can be a very cool thing if we understand it better and if we can apply it throughout. All right, that's the end. If you liked this paper, leave a comment. If you didn't like it, leave a comment. And bye-bye. See you next time.